Hello, guys. It's been a long time since I've posted a video, so it was just a bit busy schedule. So I'm back with the gravitation chapter, and in this unit, we'll study complete detailed analysis about gravitation. And first of all, we should know that the gravity or the gravitational force are two different things. And when I'm talking about gravitational force, then it is the very basic fundamental force that exists in the nature, and that is a attractional force which acts between any two masses in the universe. So if there are two masses, let's suppose there are two pencils, or there are two person which are standing nearby to each other, or even though they are standing far away from each other, then also the gravitational force of attraction would be acting between them. So this is a very fundamental force of the nature which acts between any two objects which have matter, masses. So first of all, gravitational force is a fundamental force, and this exists between any two masses. No matter how far they are kept, no matter what medium in which they are kept, and no matter that how much is their mass, gravitational force will act between them. So first of all, let us find out the basic nature of the gravitational force. And the basic nature of the gravitational force is attractive nature. So gravitational force is an attractive force, first of all. Now, Newton discovered gravity, we all know that. And he also proposed a law, which is Newton's law of gravitation. This law states that the magnitude of gravitational force acting between any two masses is directly proportional to the product of the masses and is inversely proportional to the square of distance between them. So what does this law says? That the magnitude of force, gravitational force, so I'm not putting a vector sign here because this law states about the magnitude of gravitational force. So the gravitational force magnitude is directly proportional to the product of masses, which is m1 m2, and is inversely proportional to the square of distance between them. So f is directly proportional to m1 m2 and is inversely proportional to r square. So if we replace this proportionality sign with the equal to sign, then to compensate this replacement, a constant occurs which is also called as universal gravitational constant, g. Now the value of g is 6.67 into 10 raised to power minus 11, and you can also deduce its unit by this formula itself. So you can say that the unit of this gravitational constant is Newton meter square per kilogram square. This is called as universal gravitational constant. Now why this is called as universal gravitational constant? Because it is constant throughout the universe. Anywhere in the universe, the value of g will remain the same. It doesn't depend on any medium. It doesn't depend on any physical factor like temperature, pressure, etc. So it is independent of anything, and hence that is universal gravitational constant. now what does the vector form of Newton's law of gravitation says? You can see that there are two masses, this is m1 and this is m2. The position vector of m1 is r1 and the position vector of m2 is r2. And if we connect these two masses by a line or a vector, then a vector which is pointing towards m1 is r21 and a vector which is pointing towards m2 is r12. Or we can also say that R12 is equal to R2 minus R1. And it doesn't matters in this case that R12 is R1 minus R2 or R2 minus R1. We can assume them as per our choice. And R21 is equal to R1 minus R2. Now the force F21 has a magnitude which is equal to G m1 m2 upon R21 magnitude square, and force F12 has a magnitude G m1 m2 upon R12 magnitude whole square. Now we know that any vector is represented by its magnitude and the unit vector to represent its direction. And we can also say that if two unit vectors are parallel to each other, then their magnitude is also equal to 1. So if two unit vectors are parallel to each other, so we can say that those vectors are equal. So you can see that the direction of F21 and R21 is same, and therefore we can replace the unit vector F21 by the unit vector R21. So I am writing this as R21 because F21 unit vector and R21 unit vector are equal. Okay, so F21 will be equal to G m1 m2 by R21 magnitude whole square into R21 cap. And you can also write R21 cap as R21 vector upon R21 magnitude. So finally this is G m1 m2 R21 vector upon R21 magnitude whole cube. Because you can see that already there is a square term of R21, and when we'll replace this R21 cap with this one, then another magnitude will be multiplied with this one, and therefore it is now R21 whole cube. Now similarly you can also write down that F12 will be equal to G m1 m2 by R12 magnitude whole cube and R12 vector. And if I have to write it down conclusively, so conclusively I can say that F vector gravitational force in vector form is G m1 m2 upon R cube into R vector. So this is the vector form of gravitational force. Now let us discuss some important points about this gravitational force. So first of all, among all the fundamental forces of nature, which are nuclear forces, electromagnetic forces, gravitational force is one of the weakest force in the nature. And to explain you this fact, I've taken an example of proton and proton. So in a proton-proton pair, all three forces are acting. Nuclear force is also acting when they are inside the nucleus. Gravitational force is also acting, and electrostatic force is also acting as there are charges on them. So the nuclear force is 10 to the power 42 times stronger than the gravitational force acting between them, and the electrostatic force acting between them is almost 10 to the power 38 to 10 to the power 40 times stronger than the gravitational force. So you can see that the strongest force acting between a proton-proton pair is a nuclear force, and then it is an electrostatic force, and then the weakest force acting between them is a gravitational force. So it is a very weak force. Now gravitational force is a central force. The second point is the fact that the gravitational force is a central force, and it always acts along the line joining the center of masses of the objects. It is a very important point as far as law of conservation of angular momentum is concerned. So gravitational force is a central force, which means that if we consider any two masses of any shape, and if we connect them, connect their center with a line, then the gravitational force would always be acting along that central line. It cannot act like that. This is not possible, and this is not possible. Therefore, we can always say that the torque of this gravitational force about this point and the torque of this gravitational force about this point is always zero. So we can say that the angular momentum of this object about this point is always conserved, and angular momentum of this mass about this point is always conserved. So this is a very important fact, and there would be some numericals which are based on this fact. I'll discuss them later on. Now, gravitational force is a conservative force, and hence the work done by or against it in a closed loop is zero. We all know that if we pull up a mass from the ground by a height of h, then mg would be acting on that mass in the downward direction. So if we find out the work done by mg in this process of pulling up that mass, then that work done by mg would be equal to minus mgh, because mg is acting in the downward direction while h, which is the displacement, is given in the upward direction. But if we again bring that mass back to the ground, then in the second trip you can see that mg is acting in the downward direction while h is also displacement in the downward direction. So these two are parallel to each other, and therefore the work done by mg in the second case is plus mgh. So if the work done in the first case was minus mgh and the work done in second case is plus mgh, then we can say that in the complete round path, when the object came back to the ground, the work done by mg was zero. So we can say that the displacement is also zero and the work done depends on the displacement. So this is an this doesn't prove that gravity is a conservative force, but this is an example which can show you that why this is a conservative force. So gravitational force is also independent of the medium in which masses are kept. You can see that if this is a mass m1 and this is a mass m2, and there is vacuum between them, and the gravitational force acting between them is Fg. Now if we place any medium instead of vacuum, then also the force of gravitation acting on m2 due to m1 and the force of gravitation acting on m1 due to m2 would remain the same. It also doesn't depend on the presence of any other third mass. So if we place a third mass m3 between m1 and m2, then also this gravitational force among them due to each other would remain the same. So this is a very important fact, that the gravitational force is independent of the medium in which these masses are being kept. Now the gravitational force of Earth especially is called as gravity. So many students are very confused with the gravity and gravitational force, and most often they refer them as same. So you can also now you know that especially the gravitational pull of Earth is called as gravity. Okay, so now the center of gravity is a point in a body where net gravitational force of that body can be assumed to be concentrated. This is a excellent concept, and I have already demonstrated the difference between center of gravity and center of mass in detail in center of mass chapter. You can refer the playlist of center of mass and you will find out that concept there. Now on Earth, the center of gravity and the center of mass is same thing, but in space the center of gravity and center of mass might be different. This concept also I have referred in the center of mass video, and it is the first video of center of mass. You can refer in the playlist of center of mass. Now, now let us see some numericals which are based on the Newton's law of gravitation. So in this first numerical, you can see that there is a mass m and there is another mass 4m, which are kept from each other at a distance of r. And a third mass small m is kept at a distance of x from this capital M mass. We have to find out the value of this x so that the gravitational force acting on this mass small m due to capital M, this is Fm, and this is due to F4m, is equal. So if these two forces are equal and they are, you can see that they are already opposite, then the net force would be 0. So we have to find out this value of x, or we have to find out the location of this point from this mass so that the net force acting on this mass is 0. So first of all, we can write down this net force like that Fm in the magnitude will be Gm by x square, and F4m in the magnitude will be G4m into m by this distance is r minus x. So it is r minus x whole square. Now we have to equate these forces. So Fm is equal to F4m and Gmm by x square is equal to 4 Gmm by r minus x ka whole square. So this is cancelled out, and r minus x whole square upon x square is equal to 4. So r minus x upon x is equal to 2. You can also say that it is plus minus 2, but if you'll take this minus 2, then x would come negative. And negative x means that this x is not this side and it is towards the left side. So it is not possible that any mass which is kept outside this region has a 0 gravitational pull. So this is r by x minus 1 is 2, and r by x is equal to 3, and hence x is equal to r by 3. Now I can also demonstrate this problem with a simple trick. Now this trick says, let us find out a trick. Now let us first of all draw the diagram. So this is mass m and this was mass 4m, and this was m, small m. So we need to find out this distance x such that the net force acting on this small m mass is 0. And let us suppose that this distance is y. So step 1 of this trick is that find the ratio of masses. Find the ratio of masses. Which masses? I'm talking about those masses which are already being kept before this mass was kept. So this ratio is m is to 4m. And take the square root of ratio. Step 2 is to find out the simplest ratio. I mean to say the simplest ratio. And step 2 is to find the square root of simplest ratio. So the square root of simplest ratio is 1:2. Now add this ratio. Add them. So by adding them, it is 3. And divide this complete distance r. Let us suppose that this distance is r. So divide this complete distance r into 3 equal parts. So let us suppose that after taking the ratio of the simplest ratio, after taking the root of simplest ratio and after adding them, it comes to be x. So you have to divide r into x equal parts. So one part would be equal to r by x, and in this case x is 3, so one part will be equal to r by 3. Now this distance x is proportional to the mass from which it is measured. So x is proportional to m and y is proportional to 4m. So if we know that this ratio is m upon 4m is 1:4, so we can say that the value of m after taking the square root of ratio is 1 and the value of 4m after taking the square root is 2. So I can say that x is equal to 1 part because x is proportional to the value of m, and y is equal to 2 parts because y is proportional to the value of m 4m in the square root ratio. So this x would be equal to 1 part, which is r by 3, and this y will be equal to 2 parts, that is 2r by 3. So at this distance, if we will keep this mass, then the net force acting on this mass would be 0. Let me show you another example of this trick. So let us suppose that there is a mass which is m and another mass which is 9m, and the distance between these masses is r. So we have to find out again the distance x and distance y, so that the net force acting on this small m mass is 0. So step 1 says that we have to find out the simplest ratio, and the ratio of these masses would be 1:9. Now we have to take their root. So root 1:9 is 1 by 3. Now we have to add them. So it comes to be 4. And we have to divide r into 4 equal parts. So one part would be equal to r by 4. Now we will divide this x and y according to the ratio, simplest ratio after taking its root. So x is proportional to this 1 because x is proportional to m and y is proportional to 9m. So after taking their root, x is proportional to 1 and y is proportional to 3. So I would be giving one part to x, so it is r by 4, and I would be giving 3 parts to y, which is 3r by 4. So this trick is very useful in competitive exams, and you can also find out any other question which can be done by this trick easily in less amount of time. Now let's move on the next question.